Hello, good people. Welcome to video number one of 5.6. In the previous videos, we talked about how to use the first derivative to help us analyze behaviors of the graph, or I guess behaviors of the function, by determining where the function is increasing. I guess I'll do it this way: increasing, there you go, or decreasing, or where a function might have a relative maximum or a relative minimum, right? And so the purpose of the first derivative was to tell us the rates of change of the function. If the rate of change or derivative was positive, then we knew the function was increasing. So, for example, in this picture that they give us, in this section, the function is increasing. I can see it, but I also know that it's doing that because the slopes are all positive. And the same thing over here, right? The slopes are all positive. But in this section, the function is decreasing. I know that because I can see the graph, the y values are getting smaller, but also because the first derivative or the slopes are all negative. And then we talked about how if a function switches from increasing to decreasing, or if the first derivative changes from positive to negative, well, then we have a relative max, or we might have a relative min, right? And that's what the first derivative test for relative extrema asked us to do. Use the ideas of increasing, decreasing to determine where those relative max and mins are. But now we get to the next part. And in the next part, we realize we can describe the function in another way. And in this case, we're going to talk about something called concavity. In concavity, I think of a concavity as just being what is the curvature of the graph. And so if I look at my graph here, in this section that I'm trying to shade in green, the graph is concave down. The curvature is down. Now, something nice is going to happen once we determine areas of concavity where it's concave up and concave down. So in this section, my graph is concave down. And then in this section, let's use purple. Oh, I already used purple. I'll use pink. In this section, my graph is concave up, right? And so our goal now is going to be to find intervals that describe the curvature of the graph in terms of concave up or concave down. Because whenever the graph changes concavity, then I have what's called a point of inflection, or an inflection point. I call it the point of inflection because it's easier to abbreviate point of inflection, but a lot of people call it the inflection point. And you might have heard inflection point in conversations about situations in business, like this was the inflection point of the sale, or this was the inflection point of the situation, meaning this is the magic point where things shifted, where things changed, where things improved or maybe didn't improve. But this is the magic point where the curvature changed, concavity changed, and it turns out that the second derivative is going to be our helper in determining the concavity of a graph. And so if you look at the graph that I've been filling out here, there are a lot of colors because there are a lot of things associated with a function graph, right? We can talk about the increasing parts, which are in blue. We can talk about the decreasing parts, which are in red. We can talk about relative minimums and maximums, which are in purple, those points. But now we're adding on an extra layer of concavity, which is concave down in green, concave up in pink. And the point where it changes concavity is that point of inflection. The second derivative is now going to help us figure out that change in behavior. Later, we're going to find out that concavity can also help us analyze tangent lines approximations. So if you recall, before we had used the tangent line, for example, a tangent line like this, we had used a tangent line to approximate the curve. So if I wanted to approximate the curve at x equals 1, I could use the point on the line to approximate the point on the curve. But it was going to be off, right? It wasn't going to be exact, but it was going to be a pretty good estimate. With concavity, we now realize that the tangent line approximation that occurs on a concave down part of the graph is actually an overestimate, Whereas if I were to take, oh, I don't know, maybe this tangent line approximation, and if I were to approximate the point on the graph at 5 with the point on the line, the tangent line approximation, I would see that this is an underestimate because the tangent line is under the graph. And that happens when my concavity is concave up. We'll talk about that a little bit more probably in the last video or maybe in future videos, but the idea being that concavity does have its purpose in helping me not just describe the function and how it behaves, especially the graph, but also what type of approximations I get out of it. Is it an overestimate or is it an underestimate with that tangent line approximation? So in the following video, we'll talk about how to approach this with the second derivative, and we'll look at an example on how to figure that out.